Hello and welcome back. In this video, we will look at binary decision trees with introduction to basically binary classification trees. So, we look at this data set which has basically each row is a data point. It is collected over 14 days. So, there are about 14 data points. This is just to understand this data set. There are 4 features you can see here: outlook, temperature, humidity and wind. And you can consider this our training data, and based on these 4 features and the data points provided, the decision has to be made regarding whether to play tennis or not, right. So, you can see all the S, the decision S is marked red and the decision no's are marked in black. So, we have 4 features, about 14 data points, and based on these features we have to decide whether to play tennis or not. So, how would we go about doing that using decision trees is what we are going to look in this video. The idea is to again reiterate is to make a decision as to whether to play tennis or not based on the features provided. The way you go about doing that is to split the data, split the entire data based on the features provided, eventually leading to a decision as to whether to play tennis. Okay. So, we start at a node. This is what is called a node, which contains all the data set, okay. And then we do this check whether the temperature is greater than or equal to mild. Now, just to recall, the temperature has mild, cool, hot. We go back and check here. So, there is hot, mild and cool are the 3 values that the temperature can take, categorical values. So, if the temperature is greater than or equal to mild, we decide to play tennis, otherwise we decide no, okay. So, that is the idea. And we do not have to stop with one question, we can go ahead and split further. So, we can check whether the humidity is normal or not. If the humidity is normal, then we play tennis, or if otherwise we do not play tennis, okay. Now, remember that at each node, what is basically once we start at this node with all the data, okay, and as we split the data based on this condition temperature, we will take all the data points in our data set where the temperature is greater than or equal to mild and assign it to this node, and if the temperature and all the data points where the temperature is cool, we will assign it to this node, right. This is what we want to do, and from here on again we among this data points that we have assigned to this node, we will check if the humidity is normal or not. If it is S, then we will assign it to this node here, otherwise if the humidity is not normal, then we go there, okay. So, this is the root node right here, this is the root of the tree that we have created, and the leaves, the nodes here are the leaves. So, the idea is that the as we go down this tree or if you go up this tree, which depending on how we interpret it, the leaves we would expect to have all the data that has similar decision. So, we would expect all the data where we decide to play tennis to accumulate in this node, and all the data where we decide not to play tennis to accumulate in the other node, okay. So, that is the idea behind building this tree. So, how do we go about doing that? So, just to summarize, we start with the feature in the data set and make a split based on the feature, okay. So, the split could be continuous or binary or that is categorical. So, the split is based on some condition, okay. We will see what those condition is, what that condition is later on, but just for the sake of the few slides, we will assume that we have a way of figuring out which feature to choose and how to make the split, okay. So, we choose a feature and we make a split on the data into 2, so leading to 2 different nodes. So, we assign the split data into each of these nodes, right, and we continue splitting the data based on the features. So, we can choose another feature here, again understanding that there is a way to choose a particular feature and make further 2 splits, okay. So, we can keep doing that, we can keep splitting until we come to a point where all the leaf nodes are pure. So, these are the leaf nodes, right. These are the leaf nodes, and the sense they contain only one class. So, all the data in those leaf nodes contain only one class, or when we reach a maximum depth. Okay. So, we decide that we will only go up to a depth of 3 or 4. Okay. So, then we stop after a depth of 3, or we can evaluate a performance metric upon which based on which we can stop the tree from growing further. Okay. So, this is how we build the tree, and this is using the training data, but how do we test it? So, in the sense that when the test data arrives, we pass it through the tree, and we will expect it to take a path through the tree and end up in one of the leaf nodes, and each of those leaf nodes correspond to a class, and that class will be assigned to that test data set. Okay. So, that is how we would go about building a binary regression tree. Okay. So, then here comes the question, how do we make the split? Okay. So, the split can be usually the split is based on something called information gain. Okay. We look at what that is again, but we can also use classification error, and typically these two would correspond to what is called the information gain. The entropy and the Gini index would what we would call the information gain criteria. We can also do the split based on classification error. We will look at some examples of how we would go about doing that. Okay. So, let us say we are at this particular node where we have 8 data points for which the outcome is yes, that is to play tennis, and 4 data points where its outcome is to not to play tennis, that is no. Okay. So, then we decide to make a split based on the temperature, okay, greater than or equal to mild. So, which results in 6 data points for yes to play tennis and 2 data points for no, and in this case equally distributed 2 and 2 for yes and no respectively. Okay. So, we still have not decided how to make the split and what features to choose, but we will see as we go on how to go about doing that. In this particular example is just to illustrate why using the classification error is a bad idea. So, how do we this is the equation for the classification error, 1 minus maximum of P of C, where C is the class, or the class C denotes the class. So, a number of classes can be more than 2. So, typically for a binary classification we have 2 classes, but there could be multiple classes also for this kind of algorithm. So, 1 minus max of P of C is what we would like to evaluate as the classification error. Okay. So, let us see if we look at this particular node here. So, we have 1 minus max of, so we have 8 out of 12 of S, decision S, and 4 out of 12 for decision no. So, which leads to 1 minus 8 over 12 as the classification error, right. So, this P of C is basically the proportion of data belonging to a class, belonging to class C. So, there is a proportion, the P of C is just a proportion of data belonging to class C. So, then 1 minus max of this P of C means that we have to calculate, let us say in this case we have 2 classes. If we have n classes, there will be n numbers here, and we have to choose the maximum of that, and 1 minus that will give you a classification error. When in this case it is 0.33, right. So, then so the question is how are we actually deciding on the feature, and how are we actually going to do the split. So, in this case we will see how that is calculated. So, what we have to do is then we have to look at the left and the right node. So, we are looking at binary decision trees. So, usually there is only a 2-way split. Okay. So, so we have, if you look at the left, then the classification error again using the formula 1 minus max over C P of C will give you 1 minus max of half and half, that will give you 0.5. Okay. And if you look at the classification error on the right hand side, then it is a max of 1 minus max of 6 by 8 and 2 by 8. So, that is easily chosen. So, you get 0.25. So, what we typically want to look at is the change in the classification error. So, we want something that would split that would give rise to the biggest decrease in classification error. So, what we do is after the split we calculate the average weighted average of the classification error. Here the weighted average corresponds to the weighted average of the two nodes here. Okay. So, you can call this the parent node and these two the two children node, two child nodes. So, we have to calculate the weighted average of these two. So, then how do we do that? Then we will see if you look at the classification error change. So, this is the classification error before, this is before the split. Okay. Now, we want to do it after the split. So, the weighted average in this case, so 4 out of 12 data points went to the left node. So, that is the, so that weight is 4 over 12 times the classification error in the left node. The weighting for the right node is 8 over 12, that is 8 data points on the right node, 8 over 12 times 0.25, and you will see that if you do that, then the we will see that if we do that, then the classification, the change is 0. So, this can happen when we use classification error as our metric to decide the split. So, the general idea is to consider one feature at a time and calculate the change in classification error for all of the features based on a based on a split. So, the idea is to consider each feature at a time and split the data based on the feature and calculate the change in the classification error and choose the feature that gives rise to the maximum change in the classification error. However, it is possible that when we use the classification error as a metric, then the change can sometimes be 0. So, that is what so it's that turns out to be a bad choice. So, we will see why that is so in the later slide, but so to get over this we have two other metrics that we typically use, that is the Gini index and the entropy. So, we look at entropy first. So, this is the this formula must be familiar to most of you. So, it is summation over the classes p log p again to the base 2, to keep that in mind. So, what we want to do is calculate the entropy before the split based on the feature and calculate the entropy after the split, the weighted entropy after the split based on the same feature and see which what the change is. So, let us see how that is done. So, entropy before is basically the there are two classes. So, you have to sum over all the classes. The two classes are 8 over 12 or yes and no. So, proportion of the P of C is just the proportion of data points corresponding to that class. So, 8 data points out of 12 correspond to S. So, that P is 8 over 12 log 8 over 12 and the proportion of data points which correspond to the no class is 4. So, it is 4 over 12 log 4 over 12. So, that gives rise to entropy of 0.91. Then we go about calculating the entropy on the left, which in this case 2 over minus 2 over 4 log 2 over 4, and that is about 1. Okay. And the entropy on the right hand side, again if you look at the right hand side, this is the one that is there. So, there are 8 data points there, 6 of them correspond to yes, 2 of them correspond to no, then we can this give you 6 over 8 log 6 over 8 and 2 over 8 log 2 over 8. Okay. This is summation over the classes, and just so this is basically summation over the classes P of C log of P of C. Okay. So, there are two classes, if there are n classes, there will be a n terms in that sum. Okay. So, we can do the same thing and we can calculate the entropy change as 0.0441. So, this is for one class, which is the temperature. Now, we would do the similar calculation for the other three classes, other three features, and we will see, we will calculate the same entropy change for all of them and choose the feature that gives rise to the maximum change. Of course, there are many questions here because in this particular example I have chosen, we have all of them are the features are kind of categorical in the sense there are they take from a finite set of values. So, so it is either mild. So, we can split based on anything, right. So, it can be, you can say less than hot, things like that. So, to arrive at that answer, then we have to evaluate this for even for a particular feature, we might have to evaluate this cross entropy for different values of that feature. So, if you have a continuous feature, let us say you just have temperature measured temperature in Fahrenheit or Celsius, then we have to set the right threshold on that temperature which gives rise to the largest entropy change, okay, and then we make a split based on that. So, there are different ways of calculating that, right. So, in our case we have very nice categorical labels and we can always choose among them to see which gives rise to the maximum entropy change, okay. So, this is typically how the split based on entropy works. So, let us see why we had this problem with the classification error, wherein we saw that there was no change, okay. So, that happens because let us say that you have your parent node had some entropy here, okay, had entropy value here. Let us say the children node ended up having child nodes ended up having error there and there, okay. This is a possibility. Now, we see that the weighted average can end up coinciding with the entropy of the parent node, which means that there will be no change and there will be no successive, the tree will not be able to grow the tree any further. However, if you look at your the entropy formula, which is P log P, this is the entropy base split, okay, and we also have the Gini index, which is 1 minus summation P squared. Remember, the summation is over the classes, okay. Okay. So, the maximum value of the Gini index, is can go it is 0.5, can verify that. Same thing for the classification error, the maximum value of the classification error, I will call this CE, is also 0.5. For the entropy, for a 2 class problem, okay, for a 2 class problem, the maximum entropy is 1, okay. So, if you plot all of them, then for the Gini index, it is kind of very concave, too wiggly, but you can see it is a much more smooth function than I drew here. So, you can plot that out, it is squared 1 minus P squared, you can see that how we can plot, and if you want to look at the entropy, that is it is something more like this, because the value can be to 1. They all reach their maximum value at P equal to 0.5 for a 2 class problem. Okay. You have the so the maximum entropy happens when in a particular node all the classes are equally distributed, okay. So, then that is what gives rise to maximum entropy, and for a 2 class problem we can understand when that happens, then P becomes 0.5, okay. That is a possibility. So, there is an easy way to figure out when the maximum happens. So, for instance, remember that the entropy formula, I will use that E is P log P, okay. P, think of P as a variable, then you want to find out the maximum value of phi, then you just take the derivative with its minus P log P, Tp is 0. If you do that, again this is base 2, if you do that you will figure out that that happens when P equal to 0.5, okay. You can do the same thing for a let us say a 2 class problem for Gini index, where Gini index, where I call this G is 1 minus summation P squared. Once again you can do the following dg over dp and set that equal to 0, you will get P equal to 0.5, okay. So, it is very easy to calculate, but the point is that if you use the classification error, it is because it is kind of has this linear trend, then it is possible to end up with the same total change in classification error is 0, and then there will be no way to grow the tree any further. Okay. But then if you use the other two, entropy and Gini index, then you can successfully split on the different features. If you use the entropy and entropy based information gain, then it is called the ID3 algorithm, and if you use the Gini index, it is called CART, C-A-R-T. So, this corresponds to ID3 and this one is CART. Okay. There are two different algorithms. There are different algorithms for doing this. So, one way of looking at this is a greedy search, right. So, at that particular node you are looking for the best split, instead of considering the entire tree as a whole. You just split based on the best top criteria available at that time. So, it is like greedy algorithm. And to summarize, so based on a stopping condition, we looked at different stopping conditions, one of them being the depth of the tree. Okay. At each node you find the best possible split of data based on attribute or feature. Okay. So, you select every feature, threshold that feature, okay, select a threshold based on that feature and calculate the information gain between the child nodes and the weighted average of the child nodes and the parent node, and whichever gives you the highest change in gain in information or highest change in that criterion, you will do the split based on that feature and that threshold. Okay. Now, once you have that split, then you will assign the data to the leaf nodes, 2 leaf nodes or the 2 add 2 leaf nodes, and you assign the split data to each of them, and then again start from each one of those leaf nodes, you again start doing this. Okay. So, at test time to complete to keep doing that till you reach a particular depth, or if all the elements in the leaf nodes correspond to a particular class, then you stop at that point. So, you keep going till that point, right. And for test, whenever test data comes in, you just pass it through the tree. You start at the leaf node and you keep, based on the criteria you have decided you used at that particular node, you will keep passing the data point to successive child nodes till you get to a leaf last leaf node which tells you the class. Okay. Now, it is possible that at some of the leaf nodes might not be pure. Okay. So, you might have this impure leaf nodes. Right. So, in which case you just assigned it to the you do this majority voting. So, if there are, let us say one of the leaf nodes has, say, let us say 8 yes and 1 no, for instance, whenever the test data point ends up in this particular node, you will say yes. Okay. So, that is a possibility. So, that is what we have to do. This is in brief on how to use decision trees for a binary decision tree, specifically for a classification problem. However, we can also use decision trees for regression problems, right, and we will see how we can go about doing that if you have a regression. That is possible. There is one more aspect of this binary decision trees that we have to look at, is that they tend to overfit. So, if you keep growing the tree, so you keep adding leaf nodes or child nodes to every node that you have till you get maximum purity, or in the sense till you get to leaf nodes which have only one class. Then what has happened is that you have grown a tree which fits your trained data accurately, okay, and the test data might not generalize very well. Okay. So, then that is a problem with trees, because you can always build a tree to overfit your data if you have enough depth. Okay. So, to prevent that, there are methods to what are called pruning trees. So, once you have finished growing a tree, then using the algorithm, then you go back and see if you could have stopped earlier, and then where you throw away some of the leaf nodes and you stop, so you cut down on the height of the tree. So, that is a possibility as far as binary, as far as in general binary decision trees are concerned. Okay. So, in the next videos we will look at binary regression trees also and see how they work. Also give you a small a brief mathematical motivation to how do we define a cost function for this binary decision tree. That is something also that we would like to look at. And once we have done with the regression tree and as well as the cost function for the binary decision trees. We will see how else what are the other ways to address the overfitting problem. So, we will specifically look at bagging, boosting, and we will also look at random forests. Okay. Thank you.